All right, today we're going to do something fun. We're going to break a fundamental rule of computer science. We're talking about sorting data and doing it in what's called linear time.
So, if you've ever taken a data structures class, I'm sure you've had this drilled into your head, right? That the absolute best you can possibly do in sorting is O n log n. But is that always true?
Well, the answer is no. It turns out you can totally blow past that speed limit, and by a lot, if you're willing to cheat a little. Now, when I say cheat, what I really mean is using some extra insider information about your data.
Okay, so before we can break the rule, we have to understand the rule, right? Let's talk about this so-called sorting speed limit. So that famous O n log n speed limit, it really only applies to a specific family of algorithms, comparison-based sorts. We're talking about the big names here, like quicksort and merge sort. All they can do, their only tool, is to ask a simple question over and over. Is this element bigger or smaller than that one? And if that's the only game you're allowed to play, the math is pretty clear. You just can't do better than n log n time on average.
But what if we don't limit ourselves to just those simple comparisons? What if we change the rules of the game? That's exactly where our three cheats come into play.
Yeah, we're going to look at three really cool algorithms. Counting sort, which, you guessed it, counts things. Then there's erratic sort, which works digit by digit. And finally, bucket sort, which is all about distribution. Each one of these uses a really clever trick to leverage the structure of the data itself and completely bypass that n log n barrier.
So how in the world do they pull this off? Let's get into the nitty-gritty and break down how each one actually works.
All right, first up is counting sort. Now this one is a specialist. It's designed specifically for sorting integers that all fall within a known limited range. The name pretty much gives the whole game away. It sorts by counting things up.
Okay, so picture this. You've got a whole row of bins, one for every possible number in your range. The first step is simple. You just go through your messy, unsorted list, and for each number, you just add a tally to its corresponding bin. Super easy. Then, you do a quick pass to calculate a running total. This tells you exactly where each group of numbers should start in the final sorted array. And finally, you just walk through your original numbers one last time and place each one neatly into its correct final spot. No comparisons needed.
So here's the key insight. This is the whole cheat right here. Counting sort never compares one element to another. Instead, it uses the values of the elements themselves as array indices. That's the hack. That's what lets it sidestep the comparison model entirely and get to that beautiful linear time.
Okay, next up we have radix sort. And this one is seriously clever. It sorts numbers not by looking at their total value, but by processing their individual digits, one at a time. And typically, it starts from the least significant digit, the one all the way on the right.
So here's the play-by-play. First, you sort the entire list, but you only look at the ones digit. Then, you take that newly ordered list and you resort it, this time based only on the tens digit. You just keep repeating this process, moving one digit to the left each time. And by the time you've sorted by the most significant digit, the entire array is like magic, perfectly in order.
Now, what's the secret ingredient that makes this magic work? It's one word: stability. The sorting algorithm you use for each digit pass has to be stable. What that means is, if two numbers have the same digit you're looking at, say they both end in a 7, their relative order from the previous pass is preserved. If you don't have that, the whole thing just falls apart. It's absolutely essential.
And for our final cheat, we have bucket sort. The best way to think about this one is as a scatter-gather approach. It works beautifully when you've got data that's spread out more or less evenly across a range.
Here's the four-step process. First, you set up a bunch of empty buckets. Think of them as containers for different value ranges. Second, you scatter your numbers, placing each one from your input array into its corresponding bucket. Third, you go through and sort each individual bucket, and since there should only be a few items in each one, this is super fast. And finally, you just gather up the sorted buckets, concatenating them in order to get your final sorted list.
And this perfectly highlights the core assumption, the big if, behind bucket sort. Its incredible speed comes from the hope, or the assumption, that the data is uniformly distributed. If all the numbers are spread out nice and evenly, each bucket only gets a handful of items, making those individual sorts a piece of cake. But if they all pile into one bucket, well, that's a whole different story.
Which brings us to a really important point. This incredible linear time speed, it doesn't come for free. There's always a catch. There's always a price to pay.
So let's break down this trade-off. For each of these algorithms, to get that amazing speed, you have to give something up based on a key assumption. For counting sort, your time complexity is O of n plus k, which is fantastic if your range k is small. You're assuming your keys are integers in that small range. For radix sort, it's O of d times n plus b, and your assumption is that your keys have a fixed and hopefully small number of digits d. And for bucket sort, you get that expected O of n time, but it's all riding on the assumption that your data is uniformly distributed.
And this leads us to a common myth we need to bust right now. You'll often hear people say, bucket sort is ON, period, end of story. But that's not the reality. The expected time is ON, but that's a probabilistic statement. The reality is, if your luck runs out and all your data clumps into a single bucket, your worst-case performance craters all the way down to ON squared. That is the risk you are taking.
Yeah, and there's a similar nuance with counting sort. It's not just ON, it's O of n plus k. And that plus k is a really big deal. If you're sorting, say, 100 numbers, but their values range from 0 to a billion, well, that k becomes massive. The memory and time costs of dealing with a billion-element counting array just become completely prohibitive. The whole approach breaks down.
Okay, so now that we know the cheats and we know the catches, let's get practical. When should you actually pull these tools out of your toolbox? Let's build a quick sorting playbook.
Here's your go-to guide. Counting sort? Perfect for when you have small integer ranges. Think about sorting exam scores from 0 to 100, or tallying character frequencies. Radix sort is an absolute workhorse for fixed-length keys, like standard 32-bit or 64-bit integers. It's fantastic for that. And bucket sort? That's your ideal choice when you're dealing with real-value data that you have good reason to believe is roughly uniform, something like telemetry data coming off a sensor.
So, what's the big takeaway from all this? It's that these algorithms aren't magic. They're a masterclass in trade-offs. You give up the general purpose, one-size-fits-all nature of a comparison sort, but in return, by exploiting that little bit of extra knowledge you have about your data's structure or its distribution, you get a massive win in performance.
So there you have it. You now know that the O(n log n) speed limit isn't some unbreakable law of physics. It's a rule that comes with some very specific conditions. And now you know 3 powerful, clever ways to get around it. So the only real question left is, what problem are you going to solve with them?